Do you remember the song about the quadratic formula?
X equals negative b plus...
It tells you the formula to solve any quadratic equation using only addition, multiplication, subtraction, division, and radicals. Cubic and quartic equations also have formulas using these 5 operations, but quintic equations don't. Mathematicians tried to find a formula for centuries, but it felt impossible. So a young man named Évariste Galois proved that it's impossible by combining 2 major fields of math, field theory and group theory. First of all, what are fields? Fields are a set of numbers where adding, subtracting, multiplying, and dividing any 2 numbers together gives you back something in that field. A good example is the set of rational numbers, where combining any 2 rational numbers gives you back a rational number. You know how a tree can lie in one field, but its roots lie in another? Our equations are the same, where their coefficients lie in one field, but their roots lie in another. If we want to get to these roots, we have to do what's called a radical extension. Radical extensions take us to bigger fields outside the one we started in. We consider an equation solvable by radicals if we can get to the field containing its roots through a series of radical extensions. Otherwise, we can't reach it with a bunch of radicals. But how do we know most quintics aren't solvable? That's where group theory comes in. Galois noticed that roots are related in certain ways, and swapping those roots doesn't mess with those relations. The set of swaps of an equation's roots is called the Galois group. And if an equation is solvable, its Galois group has specific properties that relate directly to our fields. Remember our radical extensions? Each time we extended, our Galois group contained fewer and fewer swaps. Each of these smaller Galois groups is normal to the group before it, which is basically saying it was extended by radicals. Galois looked at the Galois group of quintic equations and saw that one of the smaller groups was not normal to the one before it, which means they weren't connected by radicals. Therefore, there is no formula for the general quintic.